This is exercise 3I on the discriminant. Gosh, I can't speak. The discriminant on page 117 of your textbook. So, the part we're focusing on here is the X-Intercepts. How many X-Intercepts can we have in a parabola? What's the largest number of X-Intercepts we can have? 2. Yeah, exactly right. So, for example, it might look like this. In which case, I have 2 X-Intercepts. I have one right here, and I have one right here. Does that make sense? Awesome. That's what the quadratic formula tells us. It tells us what is the value of that x if y equals 0. Is there a situation where we can have one X-intercept? Is there? Are we sure? Is there, what is the situation? Exactly right. If I have my parabola and my turning point is exactly on the x, let's do a different point. Let's do that one. Then I only have one x-intercept. If my turning point is on the x-axis, it's not going to touch the x-axis anymore. So I have one x-intercept. When going through questions, you'll probably notice that sometimes you end up with a dead end algebraically. Is it possible to have 0 x-intercepts? Yeah, what situation would you get 0 x-intercepts, Lucas?
If it's not on the intercept and it's facing the opposite direction.
Good. If it's opposite, for example, in this case, there are no x-intercepts, right? The parabola goes up, continues to go up, never touches the x-intercept. So there are 3 possible answers. It's either got 2 x-intercepts, 1 x-intercept, or no intercepts at all. We can use the discriminant, which is just a subsection of the quadratic formula that we just learned, in order to try and determine how many x-intercepts we're looking at. Now, you could do this by just trying to graph it. Absolutely. But this is just trying to get like a taste. Algebraically, how do I show the number of x-intercepts? So, this section over here, this formula right here, without the if, there we go. This formula right here is a part of the quadratic formula. You'll notice that it's the one inside the square root, if you look back at your quadratic formula. So that's this part right here. B squared minus 4ac. So keep in mind, in the quadratic formula, it's the one inside the square root. I'm going to come back to that. Okay. So, if we sub in the values, now a, b, c is still the same thing. If we sub in the values, a, b, and c, to get b squared minus 4ac, and it equals 0, there is only one unique solution. Does that make sense? And same thing applies. If it's greater than 0, then there are 2 unique solutions. So in other words, if it's positive, there are 2 unique solutions. If it's negative, or in other words, less than 0, there are 0 unique solutions. Does that make sense? What do I mean by unique solutions? Tom? X-intercepts. That's what I'm looking at. The unique solutions are x-intercepts. So I'm going to apply this and then explain how it works. So first off, what are my A, B, C values? A is 1, thank you. B? Negative 8. C? 16, good work. I'm going to substitute that into this formula that I've highlighted above. So B squared, so that's negative 8 squared, minus 4 times A, which is 1, times C is 16. Are we okay with that? Awesome. What's 8 squared? 64. What's 4 times 16? 64. So it equals to 0. How many unique solutions are there? 1, which means that the graph of this equation, x squared minus 8x plus 16, has to have its turning point on the x-axis. That's the only way in order to get one solution. Does that kind of make sense? Yeah. Same idea, let's apply this again. What's my A value here? 2. B? Negative 3. And C? 4. Same thing, I'm going to apply the formula. I get B squared, which is negative 3 squared, minus 4. A, which is 2. And C, which is 4. Yep. Are we okay with that? Awesome. I'm going to go ahead and simplify it. That becomes 9 minus 4 times 2 is? Yeah, times by 4 again. Yep, minus 32. Now what's that? Well, it doesn't actually matter what it is. We just care about whether it's positive, negative, or 0. Positive or negative? It's a negative. So in this case, what does the graph look like? If what we found is the discriminant, by the way, this is another symbol for the discriminant, it's just a triangle. If the discriminant is negative, what does that mean? Sorry? So if it's negative, we're following this bottom line right here, because that says if the discriminant is less than 0. If there's less than 0, how many solutions are there? 0. If there are no solutions, it either looks something like this, or it might look something like this. One or the other. So we're focusing on how many X-intercepts are there. Does that kind of make sense? Awesome. Can anyone tell me why is there only one solution if our discriminant is 0? It's a very complex understanding from here. Why is there only one unique solution if whatever's inside the square root of our discriminant, of our quadratic formula, sorry, or in other words, a discriminant, is 0?
Because when you're solving the non-factor, it equals the y value.
I'm not quite sure what you're getting at from there, but I'll explain it. We'll see if we're talking along the same lines. Remember that a discriminant is inside a quadratic formula. It's the square root part. Remember the defining feature of the quadratic formula is it gives us two answers. That's where the plus or minus comes from, right? If the square root or the inside of the square root is 0, is there anything to plus or minus? No, we only have one answer because there is nothing to plus or minus. If whatever's inside the square root is positive, then there are two possible answers. Let's say it's like root 9. Then you do have two possible answers because you might add root 9, you might minus root 9. But if there is nothing inside the square root, there is nothing to plus or add, you only have one unique solution. What happens if it's a negative inside the square root? Yeah.
Then it can only equal positive?
So if we've got a square root negative number, does that exist? No, it doesn't exist. So if we've got a square root of negative number, there are no unique solutions. It doesn't make sense at all. So that's how we apply the discriminant. In very few cases do you have to use the discriminant. You only have to use the discriminant if you have to, let's say the question specifies it. But the discriminant kind of gives you, and this is my very odd analogy, it gives you a taste of what the burger is going to taste like. Right? It gives you a taste of what the graph is going to look like. You don't have to. You could just eat the whole thing yourself, but it gives you a taste. Does that make sense? Any questions? Awesome. I want you guys to get started on exercise 3I if you can. Remember, on Tuesday in our double, I'll only be introducing one exercise to give you guys some time to catch up. Sweet.